Welcome back to Linkfitty's Deep Dive. Today we're diving into something pretty fascinating, olmOCR. Yeah, it's this new open source toolkit. And get this, it extracts clean text from PDFs.
PDFs, huh? Well, that sounds interesting. I mean, we all know PDFs can be a bit of a pain sometimes.
Tell me about it. So much information is locked away in them, but getting it out in a way computers can use. Well, that's a whole other story.
Yeah, making that data accessible for AI research, that could be huge.
Exactly. And that's where OPS, in hoping to unlock like tons of data, potentially trillions of tokens. Think about that.
Trillions. Wow, that's mind-boggling. It's wild to think about the breakthroughs that could fuel. Just imagine how AI could understand human knowledge so much better.
It really is mind-blowing. But before we get lost in all the possibilities, let's take a step back. What makes extracting info from PDFs so tricky in the first place?
Well, it all boils down to how PDFs are designed compared to, say, a web page. They're all about that visual layout, replicating the printed page, you know.
So, it's like the computer just sees a bunch of letters on a page. It doesn't really get the meaning behind them.
Exactly. It's about how it looks, not the logical structure of the text itself.
Right. So, a PDF might tell the computer where to put each letter, but it doesn't say, hey, this is a sentence or this is a paragraph.
And figure 1 from the paper really illustrates this. You see each character stored with coordinates for rendering, but no real understanding of the text as meaningful unit. I see. So traditional OCR tools, they must have a hard time with this, right?
Oh, absolutely. They struggle to make sense of it. And even the newer models, the end-to-end ones that try to process the whole page at once, they can trip up when things get complex.
So that's where OCR comes in with its fancy document anchoring technique, giving the AI a little extra help.
You could say that. Instead of just throwing the raw image at the AI, olmOCR extracts coordinates for key elements, text blocks, images, that sort of thing.
So it's like, hey, I pay attention over here, this is where the important stuff is.
Precisely, and you can actually see how it works in Figure 2. On one side you have the raw PDF page, and on the other the OCR output, with those anchored pieces of text right alongside the image.
Fascinating. This is like giving the AI reading glasses, helping it focus on the right parts.
It's a great way to put it. And they found this significantly reduces hallucinations. Those errors where the AI makes up information, you know.
Yeah, it's all starting to make sense now. But this all hinges on a powerful vision language model, right? How do they even train something like that for this task?
That's where things get really interesting. First, they had to choose a teacher model, a much bigger, more capable AI, something to provide that high-quality output for their training data.
And they chose GPT-4, right? The big one, the powerhouse.
That's the one. But it wasn't an easy decision. They considered other options like GPT-4 Mini, even Gemini 1.5 and Claude Sonnet 3.5.
Wow, so many choices. What tipped the scales in favor of GPT-4?
Well, it came down to a balance of performance and cost. GPT-4 Mini, it wasn't accurate enough. Gemini had those issues with repeating text, you know, from its own training. And then Claude Sonnet 3.5. Way too expensive for a GPT-4 was like the Goldilocks solution. Just right.
Exactly. But even with the teacher model, they still needed tons of data to actually train OCR, like a mountain of data.
And they started with a whopping 240 million PDFs crawled from the web, right?
240 million, that's right. But of course they couldn't use all of them. First, they filtered for English documents, got rid of any PDFs that were corrupted or spammy, stuff like that.
Going to keep that data clean.
No junk allowed.
Exactly. Plus, they wanted a nice mix of document types. So they categorized the PDFs using, get this, GPT-4.
Wait, they used their teacher model to help sort the data. Clearer.
Right? And they used a specific prompt to guide it. It's amazing how much work goes into preparing the data even before the training begins.
So, what kind of categories did they have?
Oh, all sorts. Academic papers, legal documents, brochures, slideshows, even tables and diagrams. They really wanted to cover the bases.
So they wouldn't end up with a model that only worked on, say, scientific papers. They needed something more versatile.
Precisely. And Table 2 in the paper, it actually breaks down the different categories. It's fascinating to see the distribution.
I have to check that out. Yeah, but even after all that filtering and categorizing, they still had a massive amount of data, right?
They did. So they sampled it, took at most 3 pages randomly from each PDF just to bend a representative set, without any bias.
Right, because just grabbing the first 3 pages of every PDF, that wouldn't be very balanced.
Exactly. And the sampling gave them a data set of, get this, 249, 332 pages from those web PDFs.
Well, that's still a lot of pages. But that wasn't all right. They added in some digitized books, too.
You got it. Another 16,983 pages from public domain books, all sourced from the Internet Archive. They wanted to make sure the model saw all sorts of layouts and formatting styles.
Makes sense. The more variety, the better the model can adapt to different PDFs in the real world.
Exactly. Now, here's where it gets really interesting. To actually create the training data, they needed to get that text out of those pages, and they needed to do it in a way that kept the meaning. The structure, everything intact. And they used GPT-4 for this too.
Again, it's like the ultimate multitasker.
Right? They created a super specific prompt to tell GPT-4 exactly how to extract the text. You can actually find the whole prompt in Appendix A of the paper if you're curious.
Might just have to check that out. Yeah, what were some of the key things they told GPT-4 to do?
Well, they emphasized extracting the text naturally, preserving sentences even if they spanned across multiple pages, and get this, they told it to render equations in LaTeX format and tables in Markdown.
So, not just plain text, they're getting structured output that reflects the original PDS formatting. That's pretty slick.
It is. They even told GPT-4 to ditch the headers and footers, but keep the references and footnotes. Oh, and they even told it to try and read any handwritten text.
Wow, that's impressive. They really thought of everything.
They really did. And to make sure they could easily use all this data to train their own model, they specified the exact JSON schema for the output.
So each piece of data includes the image of the page, the extracted text with all the formatting, and a bunch of metadata about the page's structure.
Precisely. And of course, remember that document anchoring we talked about that's baked into this process too. They're giving GPT-4 both the image and those anchored bits of text, helping it really understand the layout.
It's amazing how much work goes into setting up the training data. It's like laying the groundwork for a skyscraper.
Absolutely. But with that foundation set, they were finally ready to fine-tune their own model.
And that's where the real magic happens.
That's where we'll pick up next time. It's incredible when you think about the sheer scale of that data set. 240 million PDFs. It's like trying to find a needle in a haystack, but instead of one needle, you're looking for thousands, each with very specific qualities.
I can only imagine the time and effort it took to sift through all that data. It really speaks to the dedication of the researchers. But before we dive into the actual training, I'm curious, how does OCR fit into the broader world of PDF extraction tools? Could you give us a quick overview?
Of course. Research in this area actually dates back to the 1950s, believe it or not. And the first commercial tools, those popped up in the late 1970s.
Wow, that's a long history. So what were some of the early breakthroughs?
Well, a big one was the release of Tesseract in 2006. It's an open-source OCR engine, and it's still widely used today.
Tesseract. Yeah, I've heard of that. But it sounds like it's not the ultimate solution, especially when you're dealing with those more complex PDFs. You're right, while Tesseract is powerful, it's really focused on recognizing those individual characters, not necessarily understanding the entire layout of the document.
So, it might be able to read the words, but it wouldn't know if a word is part of a heading, a paragraph, or a caption. Right?
Exactly, it's missing that bigger picture.
So what came after Test? How did the field evolve?
Well, we saw a shift towards more sophisticated approaches, and today we can broadly categorize PDF extraction tools into two main types, pipeline-based systems and end-to-end models.
Okay, let's break those down. What's the difference between the two?
Imagine assembly line. That's kind of what a pipeline-based system is like. It's got multiple machine learning components, each specializing in a specific task. Like one component might identify sections, another might parse tables, and another might extract figures.
So each component does its own thing, and then they pass the information along to the next one.
Precisely. And some well-known examples of these systems include Google Vision OCR ABUS Textract and PaperMage. They can be very effective, but they can also be complex to manage, and sometimes the output isn't as coherent as you'd like because each component is working kind of in isolation.
It makes sense that coordinating all those separate parts could get tricky. So, what about end-to-end models? How do they work?
These are the newer kids on the block. They take a different approach. Instead of that multi-stage pipeline, an end-to-end model tries to process the entire document in one go.
So, it's like a black box. You feed it a PDF page, and it spits out the text.
Pretty much. And they've made great strides in preserving reading order and handling basic layouts, but they can still struggle with those really visually rich PDFs. You know, the ones with lots of text boxes and images all over the place.
Oh yeah, those can be a nightmare. But haven't those powerful language models like GPT-40 also gotten really good at text extraction?
They have, but using those models directly, it can get very expensive. Remember, we talked about that 6,200 per million pages figure for GPT-4. That's a major barrier for many. Right, so that's where olmOCR comes in, aiming to provide that accuracy at a fraction of the cost.
Exactly. And it achieves that through this innovative document anchoring technique. Section 2 of the paper really digs into this, and it's fascinating stuff.
Okay, I'm ready to get technical. Remind me again, how does document anchoring work?
So remember, PDFs are all about visual presentation. They don't really care about the logical structure of the text. And document anchoring, it takes advantage of the metadata embedded in those born digital PDFs using both the text and the visual information to guide the AI.
So it's not just blindly processing the image, it's getting some extra clues about the layout of the page.
You got it. They use a library called PIPDF to extract a structured representation of the page. This includes identifying all the text blocks, the images, and their exact positions.
So it's like creating a map of the page's content.
Perfect analogy. Now, they prioritize the most relevant text blocks and images, typically those located at the beginning and the end of the document, because those often hold the most important contextual clues.
Makes sense. Those introductory and concluding sections usually provide the big picture for the entire document.
Exactly. And then they take a sample of those prioritized elements and include them in the prompt that's given to the AI along with that rasterized image of the page. And figure 2, it actually shows this whole process visually.
Let me take a look at figure 2. Okay, so on the left side we see the original PDF page, and on the right we see the output of olmOCR. And it's not just the text, it's the text with these anchors, these markers that link the words back to their locations on the page.
Exactly. It's like giving the AI a guided tour of the page, highlighting those important landmarks.
That's pretty neat. So by providing those anchors, the AI can understand the context better and avoid making those hallucination errors.
You got it. And what's really cool is that this technique, it even works well on PDFs that don't have much structured metadata. In those cases, the model relies more on the image, but those anchors still provide valuable guidance.
It's like they found a way to give the AI a basic understanding of PDF structure, even when the PDF itself isn't very helpful.
That's a great way to put it. They've bridged that gap between the visual representation and the logical structure that AI needs to make sense of it all. But of course, all of this hinges on the quality of the training data. And they were very strategic about how they went about collecting and curating that data. Remember, we talked about that massive collection of 240 million PDFs they started with.
Yeah, 240 million PDFs crawled from the web. It's mind-boggling. So, how do they narrow that down to the final training data set?
Well, First, they filtered out any non-English documents, got rid of any PDFs that couldn't be parsed or had spam content. Just basic cleaning.
Makes sense. Garbage in, garbage out, as they say.
Exactly. They also wanted to ensure they had a diverse range of document types. So, they didn't end up with a model that only worked well on, say, scientific papers.
So how did they go about determining the document type for each PDF? Do they manually go through millions of PDFs?
Well, they had a clever trick up their sleeve. They used GPT-40, their teacher model. Remember, they designed a specific prompt to guide GPT-40 in classifying each PDF into a specific category.
So, they're using AI to help them prepare data to train another AI. That's pretty meta.
It is. And this combined with a structured output schema allowed them to label each PDF according to the categories listed in Table 2. Let's see. Table 2. Okay, so they have categories like academic, legal brochure, slide ed show, table diagram, and a catch-all category for everything else. It's interesting to see how the PDFs are distributed across these types. Seems like a good chunk fall under academic, which makes sense given their focus on unlocking knowledge for AI research.
Absolutely. They wanted to make sure the model was well versed in the kind of documents that are rich in valuable information and research.
Okay, so they've claimed the data, they've categorized the PDF, and now they have a more manageable set. What's the next step?
Sampling. From each PDF, they randomly picked at most 3 pages. It's a common technique to get a good representative sample without being biased towards the beginning of the document.
So, they're not just taking the first 3 pages of every PDF, which might not be the most informative.
Exactly. This process resulted in a dataset of 249,332 pages from those web PDFs, which they combined with another 16,803 pages from public domain books they got from the Internet Archive.
That's where those digitized books come in. This adds even more variety in terms of formatting and layout styles. Right.
Absolutely. Now here's where it gets really interesting. To create the actual training data, they needed to extract the text from each of these pages in a way that preserves the meaning, the structure, all of it. And to do this heavy lifting, they turned to GPT-4 once again.
GPT-40. It's like the Swiss Army knife of AI.
So how did they use it this time?
They created a very specific prompt, a detailed set of instructions for GPT-4 on how to extract the text. And you can find the full prompt in Appendix A of the paper. It's quite fascinating to see the level of detail.
I'll have to take a look. What are some of the key things they told GPT-4 to focus on?
Well, they emphasized extracting the text in a natural way, preserving sentences even if they continued across multiple pages. They also told it to render equations in LaTeX format and tables in Markdown.
Wow, so they weren't just getting plain text, they were getting structured output that reflected the original PDFs. Formatting.
Exactly. They even instructed GPT-40 to remove headers and footers, but to keep the references and footnotes. And get this, they even told it to try and read any handwritten text.
They really thought of everything.
They did. And to ensure the data was usable for training their own model, they specified the exact JSON schema for the output.
So each data point included the image of the page, the extracted text with all the formatting, and a bunch of metadata about the page's structure and content. Precisely. And remember that document anchoring we talked about, that's baked into this process as well. They're feeding GPT-4 both the image and those anchored pieces of text, helping it really understand the layout.
It's remarkable how much work goes into preparing the training data. It's like laying a solid foundation before building a complex structure.
I couldn't agree more. And with that foundation firmly in place, they were finally ready to tackle the challenging task of fine-tuning their own model.
And that's where the AI magic really starts to happen. Welcome back to the deep dive. We've talked about the quirks of PDFs, the challenges of getting that data out, and the immense work of prepping a training data set, and now the grand final, the fine-tuning process where almost ER really comes to life.
It's like watching raw potential transform into something amazing. Think of an athlete with natural talent, and then they go through rigorous training to reach peak performance. That's what's happening here with olmOCR.
I love that analogy. Okay, so where do we start with this AI training montage?
Well, they had a strong base to work with, a model called Qwen7b Instruct. It's a 7 billion parameter vision language model, and it's already been pre-trained on a massive data set of text and images.
So, it's already got a pretty good grasp of language and visuals, right? What makes this model a good fit for the task?
It's powerful but not too computationally demanding, striking a good balance. They needed something capable of handling the complexity of PDS, but also feasible to train on their huge data set.
Makes sense. But I'm guessing they needed to go beyond that initial training, right? Fine, tune it specifically for extracting that clean text from PDFs.
You got, and that's where the carefully curated data set comes in. It acts as the guide shaping the model's abilities. Section 3.2 of the paper really digs deep into this fine-tuning process.
And they used Hooking Faces Transformers library for this, right? It's like the go-to platform for working with these large language models.
It is, think of it as a giant toolbox packed with everything you need to build, train, and deploy these powerful AI models efficiently.
So, they have the base model, the massive data set, and the right tools. What does the actual training process look like? Is it just hitting a train button and letting it run?
Not quite. It takes a lot of computational power and careful fine-tuning of the parameters to get the peak performance. They used a single node with 8 NVIDIA H100 GPUs. That's some serious hardware.
Wow, 8 GPUs. I can only imagine the processing power. What kind of parameters are we talking about here?
Things like the learning rate, the batch size, the optimization strategy used, they all play a critical role in how the model learns from the data. It's about finding the right balance, and they experimented with different settings to find that sweet spot.
Seems like fine, tuning a race car, tweaking every little detail to get the best performance on the track.
Exactly. And it's not just about the model itself. The way you format and feed the data is important too. They had to make sure the input was structured in a way that facilitated efficient learning.
So, it's a delicate balancing act, getting both the model and the data just right. But how do they know if the training is actually working? How do they track the progress?
They keep a close eye on something called the validation loss. It essentially measures how well the model is generalizing to data it hasn't seen before.
So lower validation loss means the model is learning from the training data, and then applying that knowledge to new PDFs it's never encountered before.
Exactly. And figures 3 and 4 in the paper, they show these loss curves for both the web PDF dataset and the Internet Archive book dataset. You can see this beautiful downward trend, which means the model is learning and improving over time.
I love seeing that visual confirmation that things are moving in the right direction. But they didn't just rely on numbers, right?
Of course not. They also use that side-by-side evaluation tool to manually compare the model's output with the ground truth from GPT-4.
Right. So they're actually looking at the quality of the extracted text, not just relying on abstract metrics.
Exactly. That combination of quantitative measures and qualitative assessment is crucial to ensure the model is producing high-quality output text that accurately captures the meaning and structure of the original PDFs.
Sounds like a very thorough and rigorous process.
Yeah, so once the model is trained, how do they actually put it to work in the real world?
That's where deployment comes in, which is covered in Section 4. A key focus here is efficiency and scalability. They wanted OCR to be a practical tool for researchers, developers, anyone working with large volumes of PDF. And they did this by building an inference pipeline using SGLang. Can you tell us a little bit about how that works?
Think of SGLang as a framework for efficiently executing language model programs. It lets them process PDFs in batches, distribute the workload across multiple GPUs, and even coordinate across different nodes in a cloud environment.
So in theory, you could run almost CR on a single laptop for smaller tasks or scale it up to a massive cluster of servers if you're dealing with millions of PDFs.
Exactly, that flexibility makes it adaptable to all sorts of use cases and budgets.
And that ties back to that cost comparison we talked about earlier, right? Table 3 really highlighted how cost-effective olmOCR is compared to those other options like GPT-4, Minor U, and Marker.
Yes, they achieved an incredibly low cost of 190 per million pages converted using an L40S GPU. That's a real game changer, making it accessible even for smaller organizations or individual researchers who might not have those big budgets.
It's amazing. They balanced accuracy with affordability. But robustness is just as important as cost, right? Especially when you're dealing with real-world PDFs, which can be quite unpredictable. Absolutely. They've incorporated some heuristics to make CR more reliable and less prone to those frustrating errors. For example, sometimes language models can get stuck in those infinite loops, repeating the same phrase over and over again.
Oh, I've seen that happen. It's like watching a computer go crazy.
Right. So, they simply recommended techniques to detect and interrupt those loops, making sure the model keeps moving forward. They also address the issue of rotated or skewed PDFs, which can really mess up text extraction.
So a PDF is scanned sideways or at an odd angle, almost can automatically correct for that.
Exactly. It has mechanisms to detect and adjust for those rotations, ensuring the extracted text maintains the correct reading order.
It's impressive how they've really thought through all these potential pitfalls and come up with solutions to make olmOCR as robust as possible, but ultimately the real test is how well it actually performs, right? Of course. And Section 5 is all about evaluating olmOCR, and they took a multifaceted approach. First, they wanted to see how their model stacked up against their teacher model GPT-4o. They used a document similarity metric to compare the output of olmOCR with the ground truth generated by GPT-4.
So, it's like checking how well the student has learned from the master. What were the results?
Well, Table 4 shows the comparison. olmOCR achieved an average alignment score of 875, which is remarkably close to GPT-4's self-alignment score of NV4.
That's really impressive. It means olmOCR is learning to extract and structure the text in a way that's very consistent with what's considered the gold standard.
It really speaks to the effectiveness of their training process and the quality of their data set. And to further compare, they pitted olmOCR against other popular OCR tools out there.
And that's where the human evaluation comes in, right? They had OCR go head-to-head with marker minor U and TOCR's .2, using the ELO rating system to rank them. It's like a battle of the OCR titans.
Exactly. They had data researchers and engineers at AI2 compare pairs of outputs from those different tools and judge which one better represented the original PDF.
And Figure 6 really paints a clear picture of the results. olmOCR emerges as the champion with an ELO score above 1800, significantly higher than its competitors. It's a decisive victory.
It is, and if you want to see the specifics, Table 7 breaks down the win-loss statistics showing just how consistently olmOCR outperformed the other tools.
Though it's not just accurate, it's actually better than existing methods.
But they went beyond just extracting text. They wanted to see if using olmOCR to extract the data actually leads to better performance in downstream language models.
That's a crucial point. It's not just about getting the text out. It's about making that text useful for other AI applications.
So how did they go about testing that?
They took a language model, specifically the pre-mid-training checkpoint of olmo2 1147b, and continued training it using content extracted from a set of academic PDFs. They compared two scenarios, one using content extracted with traditional methods, and the other using OCR-extracted content.
So it's like giving the language model two different sets of textbooks to study from and seeing which one leads to better learning.
That's a great way to put it, and the results shown in Table 6 are really promising across various language model benchmarks. Using olmOCR extracted content consistently led to improved performance.
So OCR doesn't just extract text accurately, it does it in a way that helps other language models learn and understand information better.
Exactly. And that's where the real impact lies. It opens up the possibility of using OCR to unlock all that valuable knowledge trapped in those countless PDFs, fueling even greater advancements in AI.
Now that's exciting, and the fact that OCR is open source makes it even better. Anyone can use it, adapt it, and contribute to its development. That open approach is so crucial for fostering innovation and making these powerful technologies accessible to everyone.
I couldn't agree more. It's really inspiring to see this project combine technical brilliance with a commitment to collaboration and real-world impact.
Well said. We've covered a lot of ground today, from the basics of PDFs to the intricacies of fine-tuning and the impressive performance of olmOCR. What stands out to you most from this deep dive?
For me, it's the attention to detail, the meticulous approach they took throughout the entire process, from crafting those prompts for GPT-4 to implementing those clever heuristics. Every step was carefully considered. It shows that building truly effective AI tools requires not just cutting-edge algorithms, but also a deep understanding of the practical challenges and a dedication to making the technology both powerful and user-friendly.
Absolutely. And the fact that they made it open source amplifies its impact, enabling others to build upon their work and push the boundaries even further. Imagine a world where AI can effortlessly access and comprehend the wealth of knowledge hidden within millions of PDFs. The potential for innovation, it's truly limitless.
A future worth striving for, and is a big state in that direction.
Well said. On that note, we'll leave you to ponder the possibilities. Until next time, LinkFit is fans, keep diving deep and remember to like and subscribe for future AI deep dives.